Alright, in sac429 problem number 3, we're supposed to find the electric flux outward through a flat circular sheet where the electric flux is associated with an electric field of 2250 newtons per coulomb, first in the plus x direction, then in the plus y direction, then in the plus z direction. We're going to be using the expression flux is equal to E dot A, where the electric field vector will be that 2250 newtons per coulomb times I in case A, times J hat, the unit vector in the y direction in case B, and times K in the case C. The A vector, that's the area vector, is what's somewhat new. It's a vector that has magnitude equal to the area of the sheet in question, in this case a flat circular sheet, and it's pointing in the direction outward from the face of that area, or it's in the direction in which that area is facing, or that sheet is facing. The magnitude is easy enough to get, just the area of it. That'll be pi r squared, which in this case is pi times 0.036 meters squared, or 0.004071 too many sig figs. It's just an intermediate result, so I'll drag along some extra sig figs there. Meters squared. And now I got to get the direction associated with that. They say the direction is in the same direction as the position vector for the center of the circle, where the center of the circle is at this position. So the position vector is a vector that extends from the origin to that position, and such a vector can be expressed as r is equal to 4 centimeters times I plus 6 centimeters times J plus 5 centimeters times K. And what we want to do is find a unit vector in that same direction and then multiply A times that unit vector, and we'll have the area vector that we want. That is a vector that has magnitude A and it's in the same direction as this vector R. The unit vector R hat is going to be equal to the vector R itself divided by the magnitude of the vector R, where the magnitude of vector R, that R, is going to be given by the square root of the sum of the squares of the components. I'll call this x component of the position vector just x, and the y component I'll call y. The z component I'll call z. Then the magnitude of the original vector R, the length of that vector, is given as x squared plus y squared plus z squared, all to the 1/2. Take the square root of all that. So that's going to be equal to 4 centimeters squared plus 6 centimeters squared plus 5 centimeters squared, all to the 1/2, or evaluating that, we find it to be 8.775 centimeters. And now we're in a position to get R hat. Say it's equal to R itself 4.00 centimeters times I plus the 6.00 centimeters times J plus the 5.00 centimeters K, all divided by the magnitude of R, which we just found to be 8.775 centimeters. You divide a vector by a scalar by dividing that scalar into each one of the components. You note the centimeters will cancel out in every case. So the unit vector, suppose to have unit length with no units, and indeed it will have no units. And we get 0.4558 times I plus pure number 0.6838 with no units times J plus the 0.5698 times K. You might want to check and verify that this is indeed a unit vector by taking the square root of the sum of the squares of the components, and you better get something very close to 1. To 3 sig figs should turn out to be 1. So now we're in a position to get that area vector A, which is its magnitude times its direction, and the direction is just a unit vector in the direction of R, which is what we just found. So the area, we got 0.0040715 meters squared. Read that from up here. And the unit vector we just found. And there it is. Now this is just multiplying a vector by a scalar. And we take this number, multiply it times that number, same number times that number, same number times that number, keeping the I, J, K in there, and I get for the area vector A 0.001856 meters squared times I, that's that times that, plus 0.02784 meters squared times J plus 0.02320 meters squared times K. There's our area vector. And now we're in a position to calculate the flux. Remember that was going to be E dot A for part A. The E is going to be the given value uh, 2250 newtons per coulomb, times I, making it a uniform electric field in the positive x direction, because the unit vector I is in the positive x direction. And what we're supposed to be calculating here is the electric flux, phi, or phi sub E if you prefer. I'm just going to write it as phi, E dot A, which is the E vector, 2250 newtons per coulomb, dotted into the area vector, which we found to be 0.001856 meters squared times I plus 0.002784 meters squared times J plus 0.0023320 meters squared times K. And this is actually a pretty easy dot product. I and J are perpendicular to each other, so this part dotted into that part gives 0. Same thing for I and K, so this part dotted into that part gives 0. All we have left is this part dotted into that. I dotted into I is 1, so it's just the product of these two values. Phi is 2250 newtons per coulomb times 0.001856 meters squared, which turns out to be 4.18 to 3 sig figs. We'll go ahead and round it this time. Newton meter squared per coulomb, the unit of electric flux. It's 4.18 Newton meter squared per coulomb. Alright, part B. E is same magnitude, but this time in the J direction, because they said it's in the plus Y direction, so I multiplied times a unit vector in that plus Y direction, which is J hat. And then phi itself is E vector dotted into A, just as before, and this time that's 2250 newtons per coulomb J dotted into the same unit vector that we had before, the area vector. I shouldn't say unit vector, dotted into the area vector, same area vector that we had before. I'll write the whole thing out, 0.001856 meters squared times I plus 0.002784 meters squared times J plus the 0.002320 meters squared times K. So the electric flux in this case, J dotted into I is 0, J dotted into J is 1. So that term matters, and I get 6.26 Newton meters squared per coulomb from that one, but the J dotted into K. J and K are perpendicular to each other, so the dot product is 0. And it's that middle term that gives us the entire answer. There's the flux in the case of an electric field in the positive Y direction. So part C, we wanted the electric field to have a magnitude of 2250 newtons per coulomb, but be in the plus C direction. So that would mean it's at 2250 newtons per coulomb times a unit vector in the Z direction, namely K. And the flux is still E dotted into A, same as before, we just have a new E, and that's going to be equal to 2250 newtons per coulomb times K this time. That's why it's a new E, just same magnitude but a different direction, and then dotted into that vector A, which I'm just copying down from the last time we used it. And let's see, the K dotted into I gives us 0, K dotted into J gives us 0, K dotted into K gives us a 1. It says this 2250 newtons per coulomb times the 0.2320 meters squared that we're multiplying, and I get 5.22 Newton meter squared per coulomb for the flux through that circular sheet for the case when the electric field is a uniform electric field in the plus z direction.